Hello everybody, and welcome back to another geometry lesson. Today we're taking a look at section 10.3, using chords. Now remember that a chord is going to be a line segment that goes from one end of the circle to the other end of the circle. So for instance, this here we could call chord AB. But here's something interesting that we may notice. What happens if I draw a chord that looks almost the exact same as the other one? What if I drew two chords that are the same length? Well, if you have two chords that are the same length, that means that those chords would be congruent, right? The rule is, if you have two chords that are congruent like this, look at the measures of the arcs AB and CD. It looks like both AB and CD are about the same as well. Folks, as we've learned, a chord and an arc are interconnected. So this chord being the same as this chord means that arc AB is congruent to arc CD. That's what the congruent corresponding chords theorem says. The congruent corresponding chords theorem says, in the same circle, or in congruent circles, so this could also work if you have two circles that are the same, two minor arcs are congruent if and only if their chords are congruent. I'm going to shorten if and only if to IFF. That just means that it works both ways, forwards and backwards. If and only if their corresponding chords are congruent. Again, that if and only if makes this a bijunction. It works when you read it forwards and backwards. Cool. Now, we do have some other theorems we're going to talk about, but I'd like us to practice the congruent corresponding chords theorem with exercise 1. So in exercise 1, we have two circles, and we're asked to find the indicated measure. In this case, the indicated measure is the measure of arc GF. So we're trying to find this green arc. But how do we do that? Well, first things first. We see that these two chords, GF and JK, are both congruent. So if they're on the same circle, or if they're on congruent circles, that means that the chords are congruent. That makes the arcs congruent. Here's the thing though, we don't know if these circles are congruent, right? Well, that's where these come into play. A line segment that goes from the center to the edge is a radius. And if two radii are congruent, the two circles are congruent. Which means, yes indeed, these two arcs are in fact the same. Since JK is 80 degrees, GF is also 80 degrees. Let's take a look at example B. In this one, we're asked to find the measure of arc AB, but there's a problem. We don't really know anything about this arc, right? Okay, well what could we do at the very least? Take a look at the two chords that make up AB and BC. We see that these two arcs look the same, but the chords themselves are both the same length. In other words, the chords are congruent. The rule is, if the chords are congruent, then the arcs are congruent. So that means that arc AB is congruent to arc BC. How does that help us? Well, we have to be a little bit creative here. We don't know what arc AB is, but we could call it x to say that it's an unknown. And we don't know what arc BC is, but if it's the same as AB, wouldn't this also be x? That means we can set up an equation to solve for x. Remember that all the arcs across a circle add up to 360 degrees? So 360 equals 110 plus this x plus this x, so plus 2x. We can solve this to find the measure of arc AB. First we would subtract 110 from both sides to get 250 equals 2x. Then we can divide by 2 to get x is 125. Since x is arc AB, we can see that arc AB is 125 degrees. Spectacular. Let's take a look at the next couple definitions. The next two definitions are the perpendicular chord bisector theorem and the perpendicular chord bisector converse. Now, it's a lot of words, but let's go in detail and see what we can do. I want to make two chords, but here's the thing. I want one of the chords to be a perpendicular bisector, meaning it's perpendicular to the first chord, and it cuts the first chord in half. So let's say I drew this chord up here, like so. I'll call this chord A, B. If I want to cut this chord exactly in half, I have to find around the halfway point. So if I'm looking at this chord, it's about 1 8 inches. So half of that is going to be just over halfway across. The chord I'm looking for is going to go through there. And if I want the chord to be perpendicular, I'm trying to make it at a right angle with the original. So I'm going to try my best to get it as accurately as I can. But I think this looks pretty perpendicular. It really is close enough. Let's call this chord CD. Now, what have we just done? We've cut the chord in half so that these two pieces are congruent. And we've made it a right angle, or we were supposed to have made it a right angle, if we drew it accurately. What does DC look like? Does it just look like any other chord? It actually sort of looks like chord DC goes through the middle of this circle, right? We'll call this E. What do we call a chord that goes through the center of a circle? Well, we call it a diameter. So it turns out, if you try to make a perpendicular bisector to a chord, you get a diameter every single time. No matter how you place your chord, if you are cutting it in half perpendicularly, you're going to make a diameter. And that's what this theorem says. The theorem says, if a diameter of a circle is perpendicular to a chord, then it bisects the chord. It cuts the chord in half. But I'm putting a ... here because there's one more piece of this puzzle. Remember from our last definition, we mentioned how chords and arcs are linked. If you have a chord that's congruent to another one, the arc is congruent to the other one. If you have a small chord, you'll have a small arc. If you have a large chord, you'll have a large arc. If we cut our chord in half, our chord being AB, what do we think happens to arc AB? it looks like the arc is also cut exactly in half. This little arc from A to C is the same as the arc from C to B. So not only does it bisect the chord, it also bisects its arc. So having a diameter is really useful here, because if you have a diameter that cuts a chord perpendicularly, it cuts that chord in half and the arc in half. Nice. There's also a converse to this. A converse which basically says, hey, if you've got the situation going on here, that bisector has to be a diameter. It says, if one chord of a circle is a perpendicular bisector, of another chord, then the first chord is a diameter. It has to be. So anytime you see a chord cutting another chord in half, and it's perpendicular, that thing that's cutting it in half is a diameter, no matter what. So let's flip the page and take a look at example 2. In this diagram, it's a bit trickier. We're asked to find two things. First off, we need to find the measure of line segment HK. Looking at the diagram, what is line segment HK? Well, since it's a line segment that goes from one end of a circle to another, but it doesn't go through the middle, this is just a regular chord. Well, what do we know about this regular chord? We can see that line segment JL cuts through it perpendicularly. But what's special about JL is, isn't that a diameter because it goes straight through the middle? The rule is, if there is a diameter that cuts through a chord perpendicularly, that chord has to be cut in half. So that means HN is one half and NK is the other half. Since NK is 14, that means HN is 14. So what's the entire green line segment if both sides are 14? Well, we can see that the measure of HK, that entire segment, should be 28. Perfect. Now it's asking us to find the measure of arc HK. And the good news is, if we know our chord is being cut in half, we also know that our arc is being cut in half. These two mini arcs, H to J and J to K, are congruent. Well, we don't know what either of these mini arcs are, but we know that we can set them equal to each other since they're both congruent. So, we can say this. We can say 2x minus 8 has to equal 127 minus x because congruent arcs, their measures are equal. From here, we just need to solve algebraically. So I'm going to move the x over to the left side by adding it. Adding that x changes this to a 3x. And I'm going to move the negative 8 to the right side by adding 8. We get 3x equals 135. From here, we just have to divide both sides by 3, and we get what x is. X is 45. But we're not looking for what x is, we're looking for the measure of arc HK. So, we can use this measure of x, plug it in to either of the arcs, and we'll find half of HK. Let's plug it into this one right up here, the 127 minus x. If we know that the measure of arc JK equals 127 minus x, and x is 45, 127 minus 45 is going to give us 82. Now remember, arc JK is half of the arc we're trying to find. So if half the arc is 82, what's the full arc? Well, we just multiply that measure by 2. 2 times 82 gives us 164 degrees. Very nice. We've got one last definition we're going to do, and then 2 more examples. The next definition is the equidistant chords theorem. Now, this is going to require us to remember what on earth equidistant means. Equidistant means equally spaced apart. So, for instance, the number 15 is equidistant from 10 and 20, because it's equally spaced apart from the two of them. For the equidistant chords theorem to work for us, we need to do the following. Start with the center of your circle. And I'm going to go ahead and call this point, let's call it E. Like so. Next, I want to draw 2 chords that are about the same distance away from E. So I'm going to draw one chord on top, like so. And I'm going to draw a chord on the bottom, like, that should be about equidistant. Yeah, that's close enough. And I'm going to call these chords A, B, and C, D. Now, remember what equidistant means. It has to be the same distance away from both lines. To find the distance between a point and a line, we look for the shortest distance. And we know the shortest distance between a point and a line, all the way back from Unit 1, is going to be the perpendicular line segment to it. That is the shortest distance. And we could repeat this for chord AB. We look for the shortest possible distance. It's going to be the line segment that is perpendicular to it. Now get this. If we say that these two distances are the same, what does it look like is true of the chords? The chords look to be about the same length. So, chords CD and AB are congruent. The rule is, 2 chords are congruent if and only if they're equidistant from the center. That's what the equidistant chords theorem says. So, in the definition we say, if 2 chords on the same circle or congruent circles are equidistant from the center, then they are congruent. If 2 chords on the same circle or congruent circles are equidistant from the center, then they are congruent. Very nice. Let's take a second to flip to exercise 3. Now, I'm going to warn you. Exercise 3 is a lot tougher than some of the other ones that we have seen so far. So we're going to walk through this one together. But be warned, we're going to be pulling in a lot of information from other units. We are told, in this diagram, QR and ST are both 16. So we have 2 chords that we know are both going to have a measure of 16. This one's going to be 16, and this one's going to be 16. CU is marked as 2x, CV is marked as 5x minus 9. So there and there. And just from that, we need to figure out the radius of this circle. We're asked to find the radius here. What a bizarre thing to find. However, we can do so. Remember we just said, if two chords on a circle are congruent, what does that mean about their distances from the middle? Well, it means that they're congruent. So 2x and 5x minus 9 are congruent to each other. Will this help us find the radius? Maybe, but just know, neither 2x nor 5x minus 9 is that radius we're looking for. This might just help us along the way. So we can set 2x equal to 5x minus 9 and solve. We can subtract the 5x from both sides to get negative 3x equals negative 9. We divide by negative 3 on both sides, we get x equals 3. So if x equals 3, how long is this blue line segment? Well, if x is 3, then 2x equals 6. And similarly, down here, 5x minus 9 would be 6, because they're congruent. Now it's time to do a little bit of a leap of faith. Unfortunately, even though we know a good portion of the radius, even though we know a good portion of the radius here is 6, we don't know that entire segment because this last bit is left out. Instead, I want to use something a bit different. You see how we have a right angle here? Is there a way we could turn this into a right triangle? Well, it turns out that we can, and we can make a radius while doing so. Connect up points Q and see what you get. You end up with a right triangle. Now, if we can figure out what QC is, that will be our radius, R. We know two sides of the triangle at this point. We know that this short leg is 6. We know the hypotenuse is R. If only we knew that little red segment. But wait a second. We learned that if you have a perpendicular chord, that is the diameter, then the chord has to be cut in half, right? And wait a minute, in this diagram, we do have a diameter perpendicular to chord QR. Because WX is a diameter, and because it's perpendicular to this red line here, we know that QU and UR are both going to be the same. In other words, if the entire line segment is 16, this portion of the line segment is 8. This diagram is a bit messy, so let me write it over here so we can see it a little bit better. We have a line segment that is 8 units long. We have a line segment that is 6 units long. And we also have a radius, R. Finally, we happen to know that this triangle is a right triangle. So, how could we solve this? How could we solve for R? Well, we can use the Pythagorean theorem. The Pythagorean theorem says a squared plus b squared equals c squared, where c is our radius r. So, we can rewrite this as 8 squared plus 6 squared equals r squared. Let's do this. 8 squared is 64. 6 squared is 36. And we know that has to equal r squared. Since 64 plus 36 is 100, our radius squared is 100. We just have to take the square root of both sides, and we see, since the square root of 100 is 10, our radius for circle C is 10. I would recommend going back through the video and re-watching this problem in particular, because there's a lot of moving parts in it that I want to make sure we know how to do. Let's take a look at the last examples, which are proofs. Now, whether or not there are proofs on our test here, there may be one on the final. So I want us to get more practice with proofs. Spin a second. We want to use the diagram to prove each part of the biconditional in the congruent corresponding chords theorem. What does that mean? Well, it's telling us we have to prove that this theorem exists without using this theorem. We have to show that if two chords are the same, two arcs are the same. And if two arcs are the same, two chords are the same. Sounds easy enough. All we're given to start with is one congruency. That line segment AB is congruent to line segment CD. Now remember, we're trying to prove that the theorem works. So we cannot just go ahead and say, oh, the theorem says that we can just do this. We're trying to prove this theorem in the first place. But when we look at the diagram, we get a bit stuck. So it might require us to sort of take a leap through the problem backwards. Here's what I mean. Let me redraw this circle a bit bigger. I have my trusty compass here, with the center right here, and we'll say that it's this circle here. We know how to make a circle. And across this circle, we had the following lines. We had what looked to be something of a triangle on the left, and a similar looking triangle on the right, right? Well, we know that if two triangles are the same, which is really what we would like here, then we know that their angles will also be the same. So if we could somehow show that these two triangles are congruent, we would know that their angles are congruent. And what do we know about angles and arcs? Well, if two angles are congruent, then their arcs are congruent. So here's what I mean by working backwards. We want to show that this arc and this arc are congruent. We know we can do so by making these two angles congruent. We know these two angles will be congruent if the two triangles are congruent. We just got to figure out how to prove these two triangles are congruent. Let's take a look and see what we can do. So, looking at the diagram, we know that one part of these triangles are congruent, just one side. If we knew some kind of theorem to help us show that these two triangles are congruent, we could use it. But it's not enough to just have one side congruent. So what else can we assume about these triangles? Let's look at side DP, for instance. What would we call that side? Well, since it goes from the middle of the circle to the edge of the circle, we know that it's a radius, r. What do we know about PA? Well, it goes from the center to the edge of a circle, so it's a radius, r. Hang on a second. Can't we say the same thing about PB and PC? These are just a bunch of radii. We happen to know that all radii in a circle are congruent to each other. So we have two triangles where all their sides are congruent. Let's jot this down. So first things first, we know that PA is congruent to PB. Whoops. There's congruent to PC. There's congruent to PD because they're all radii. The definition of a radius says that all radii in a circle are congruent. If these are all congruent, could we show that the two triangles are congruent? That triangle DPC is congruent to triangle APB? Well, remember that we absolutely can. In Unit 6, we talked about all those triangle congruencies, and one of the big ones was two triangles are congruent if all sides are congruent. This is side, side, side triangle congruence theorem. Very nice. And, like we said before, we did our little planning here. If the two triangles are congruent, that means these central angles are congruent. So, we can say that angle DPC is congruent to angle APB because, well, if triangles are congruent, their angles are congruent. The reason we give for this is corresponding parts of congruent triangles are congruent. CPCTC. Corresponding parts of congruent triangles are congruent. So, we've done it. We've proved that these two angles are the same. But that means these are the central angles. We learned in 10.2 that if you know a central angle, the arc is congruent to that central angle. So if we have two congruent central angles, we have two congruent arcs. Arc AB and arc DC are congruent. Very nice. And again, that's just the definition of a central angle. So here's what I'd like you to do. I want to let you know that this next proof is almost the exact same thing, just sort of backwards. This time we're starting by knowing the arcs are congruent, and we're finishing off with the line segments being congruent. I want you to give this one a shot using the previous proof as a frame of reference. Pause the video and try it out. How'd you do? If we take a look at this proof, starting with the fact the two arcs are congruent, if these two arcs are congruent, we can work backwards. When the arcs are congruent, the central angles are congruent. Just like last time, we know that all the sides of these triangles are radii, so this is congruent to this, is congruent to this, is congruent to this. The only difference is, to prove these two triangles are congruent, all we have is a side, an angle, and a side. So we have to use side, angle, side congruence theorem. But if the two triangles are congruent, our line segments are congruent as well. Thank you so much, everybody. That will conclude our notes for today. Have a fantastic rest of your day.